In another exciting episode of Stats and Stuff, we're at Week 7, Lecture 2, One-Way Repeated Measures ANOVA. So when do you use one-way repeated measures ANOVA? Well, you use it when you have one nominal or ordinal within subject's independent variable. It's got 3 or more levels, and you got a DV that's interval or ratio. So the easy way to think about it is it's basically paired t-tests when you've got an IB that has 3 or more groups. Okay, that's when you use repeated measures ANOVA. So some examples. Do levels of depression change from week to week for 20 persons in a bereavement support group? So you measure them each week for a 1-month period. That'd be 4 total measurements. The same people over time, so it's a within design, and you're just looking at changes over time, which is your IV. All right, so then we've got the effect of annoying sounds on concentration levels. This is going to be the one we analyzed for fun. So concentration levels is operationally defined as the numbers of errors on a simple 50-item math test. You have them trying to do simple math problems while you're trying to annoy them with noise, wherein each participant experiences all levels of the IV in a counterbalanced order. So you mix up the order that they get: crying newborn, nails on chalkboard, or chewing tinfoil, and they're trying to do math problems, and you count the number of errors, and you assume where the errors are higher, they have worse concentration. Probably true. So what are the assumptions of repeated measures ANOVA? They are a little unique. One is dependence. So the participants in each level of the IV are the same, they're pairs, or they're somehow matched. Basically, it means you've got a within subject's design. If you've violated this assumption, you're using the wrong ANOVA. You should be using the one from last week, between subjects ANOVA. So normality, the usual one. The DV is approximately normally distributed for each level of the IV. Okay. So how do we test that? We look at the skewness statistics for the DV for each independent variable group, and you see, is the skewness statistic absolute value less than 2? If so, cool, normal enough. You want all groups to be normal enough. So turns out, of course, just like between subjects ANOVA, repeated measures ANOVA is also robust to deviations from normality, meaning it doesn't get too messed up if things aren't too whacked out. So on the left here, I have an example of distributions, 4 different ones that are normal. So they are all approximately normal, but you can see they differ in another way, and that's going to be one of the next assumptions, the heterogeneity. And on the right, you've got things that are not normal. So these ones the ones on the left would meet this assumption of normality. They'd end up violating the heterogeneity assumption. The ones on the right are going to violate normality. They're just skewed, and they're not even kind of normal. So this one's new, I think. Yeah, this is new to you guys. Sphericity or circularity. It is the assumption that of homogeneity of variance and covariance. And you guys have no idea what a covariance is, and that's okay. You don't actually need to. I'll give you a short way to tell what it is. So homogeneity of variance you're familiar with. That's when the spread of scores is approximately equal across all IV levels. So the spread's about the same. That's old hat. There's the new part. Homogeneity of covariances is the second part of the sphericity assumption. And that is that if you correlate any 2 levels of the DV between any 2 levels of the independent variable, so their scores, you get about the same size and magnitude of correlation as any other 2 levels. So it is that the relationship between any 2 levels happens to be similar. And it's frequently violated, so frequently violated that they actually build in a test that you can use. You can interpret the results of instead of the regular ANOVA that assumes this, because it's violated so darn frequently. So it's kind of like that t-test, independent t, where like they know it's violated, so they just build in the test right there, and you just read a different line. Same thing in this case. So you test it using something called Mauchly's test of sphericity. SPSS spits it out. That's Mauchly right there, apparently. And the null of this test is that the sphericity assumption is met. That is, you have sphericity. So it's, again, one of these weird instances where you don't want to be rejecting the null hypothesis. So here's the rules. If Mauchly's sig is greater than 0.05, the sphericity assumption is met. You're maintaining that null of sphericity. However, and you will interpret the sphericity assumed ANOVA results. So the line that says sphericity assumed is what you'll use if Mauchly's sig is greater than 0.05 to interpret your ANOVA. All right, here's a however. If Mauchly sig's less than 0.05, that means you violated the sphericity assumption. Could be the homogeneity variance, could be the homogeneity covariance. The homogeneity covariance is usually the one that's violated because people do things over time. And things that are closer in time are more strongly correlated than things further in time. And so it's frequently violated. So what do you do if Mauchly sig's less than 0.05 and you violated this assumption? Do you give up? Do you not graduate? Nope. So the result is you get type 1 error inflation. That's the usual thing that happens when you have you get lower power or you have type 1 error inflation. So that's the result. But if you violate sphericity, just interpret the epsilon adjusted results, which are these things that SPSS prints out. We're going to use Greenhouse Geyser this week. There's also Hunfeld and lower bounds. They're printed there. They don't assume that sphericity is met, so you can use them. So hope is not all lost. The other thing you could do is if you look above repeated measures ANOVA in the matrix O statistical test, you'll see that there's something called Friedman ranks in there. And Friedman ranks test, it's got more words in it, I think, but Friedman ranks test is a non-parametric equivalent of repeated measures ANOVA, and you can use it instead to analyze your data if things are really, really bad. Like that example where the normality was super crazy in that earlier slide, where everything was skewed, you might end up using your Friedman ranks. So, just like last week with between subjects ANOVA, except it'd be paired t-tests here, why don't I just do a bunch of paired t-tests and call it a day, right, and graduate? Well, if a within subjects IV has, let's just say it's 3 levels, right, and you want to compare them all to each other, of course, because you would use paired t-tests to do that, A to B, B to C, C to D, or A to C, etc. You'd have to compute 3 different tests. Each one is a mean-to-mean comparison that would have an alpha level of 0.05 in that paired t-test. So, for example, here's the one with the annoying noises. So you'd have one test there, crying newborn to nails on a chalkboard. We're trying to do, you'd be comparing the errors they made under those 2 conditions. That's alpha of 0.05. The next one you do is probably crying newborn versus chewing tinfoil. That's another alpha of 0.05. You can probably tell where this is going. Nails on the chalkboard versus tinfoil. That's another 0.05. Together, across this family of tests, you've got an alpha level of 0.15 family-wise. So we call that your family-wise alpha level. You got a 15% chance of making a type 1 error, not a 5% chance. So this is type 1 error inflation again. So you have a 15% chance of making a type 1 error if you were to do separate t-tests versus doing the ANOVA. The ANOVA controls for it in one test. And again, we call that your family-wise alpha level. It's bad, you don't want to do it. And it would be inflated. And so your alpha level would be higher than your stated alpha level, which is a no-no in research. All right, so how do you write hypotheses? Exactly the same as between subjects ANOVA, if that makes it easy for you. The null hypothesis is, again, that the means of all the groups are equal. So there's your null. Mean of group 1 is mean of group 2 is equal to mean of group 3, etc., and so forth. Your alternative is that they're not all equal to each other. So guess what? This is also an omnibus test. If any group differs from any other group, you'll be rejecting the null. So the little n at the end there just means keep going until you run out of IV levels. So if you got 4 levels, you'd also have, x bar is equal to x bar 4, right? And if you had 5 to x bar 5, you just keep going. So it is an omnibus test. It tests multiple things at the same time. And the hypotheses for the ANOVA omnibus test are always two-tailed. It's things are all equal versus things are not all equal. That's all you get. So in the example on the prior slide, the ANOVA isn't going to inflate the type 1 error rate because it tests if any of the 3 levels of annoying noises differ from each other at the same time rather than doing separate paired tests. So that's how you really do only have a 5% chance of making a type 1 error if you do repeated measures ANOVA versus if you do a bunch of paired t-tests. And you're going to see we end up doing a bunch of paired t-tests, but we control for it in a different way, your alpha inflation. So the omnibus ANOVA will be significant if any group differs from any other group. And that's the benefit of doing ANOVA versus a bunch of separate t-tests. So your decision rule, you first are going to actually look at Mauchly's test, because that's going to be sort of the signpost that tells you which line of results to read in the ANOVA table. So look at Mauchly's test of sphericity. And if Mauchly's sig is greater than 0.05, you've met the sphericity assumption. So you get to interpret the line in the ANOVA within subject's results that says sphericity assumed. So it's just like independent t, well, it's similar to independent t, right? If your Mauchly sig, however, is less than 0.05, you violated the sphericity assumption. And my recommendation is just use the line that says greenhouse geyser. So there is Untitled and a couple others, but greenhouse geyser is the most appropriate for the one we're doing. So once you get your line, either sphericity assumed or greenhouse geyser, that you're going to use in your ANOVA results, you will interpret that line using the following rules for the ANOVA. If that ANOVA sig is less than 0.05, reject the null. I love two-tailed ones. They're simple, right? And what's that mean? All the levels of the IV are not equal on the DV, right? At least one group differs from at least one other. If your ANOVA sig is greater than 0.05, you retain the null. There's no differences. Not even one group differs from one other group, okay? So they're basically equal. So if you reject that null, which levels differ? All I know is one differs from the other. Is it A to B? Is it B to C? Or A to C? Is it B to C? You don't know. You have to follow it up, just like with between subjects ANOVA with post-hoc tests, but there's no Tukey this time. So let's talk about the post-hoc tests for repeated measures ANOVA. These are the after-the-fact tests. That's what it means in Latin. When you reject the null for ANOVA, it only tells you that the means for the IV levels are not all equal to each other. It could be one differs from just one other one. It could be they all differ from each other. Two of them differ from the third. You have no idea, right? So you have to run these additional post-hoc tests to determine exactly which levels or group means differ from each other. There is no Tukey for repeated measures ANOVA. Bummer. And so instead you got to use a series of paired t-tests. And that is going to do the A to B, the A to C, and the B to C comparisons. But didn't I just tell you that's bad because you get type 1 error inflation? Yes, you were listening. So to control for type 1 error inflation, you evaluate the statistical significance of each of these paired t-tests using a modified alpha level called the Bonferroni corrected alpha level that's going to keep your overall alpha level at 0.05. And how's that? Well, here's the formula. It's real simple. You take the alpha level you want to keep, 0.05, and you divide it by the number of tests that you're going to be using that to determine the statistical significance of. So 0.05 divided by 5 tests, you'd be evaluating each paired t-test at alpha of 0.01, for example. So, but here's an example here. So if you've got an IV with 3 levels and you're going to do these paired t-tests because the ANOVA was significant, you've got 0.05 divided by 3, you'd be using 0.017. So the sig would have to be less than 0.017 for you to say, yes, these two groups differ from each other on the DV. So in that way, you maintain a 0.05 alpha level. So you will use alpha of 0.017 on our problem that we're about to do instead of 0.05 to interpret the paired t statistical significance when you got 3 groups. So the measure of effect size is eta squared this time, or n squared, whatever you want to call it. It's defined as the sum of squares of the independent variable, and it is a within independent variable, divided by the sum of squares total. We just learned those last week, what sum of squares was. It's something that SPSS spits out in a table. If you really want to know, show up at office hours. So how do you calculate sum of squares total? Yeah, it doesn't give it to you, and it's not accurate in what SPSS spits out. You actually got to calculate it most of the time. You take the sum of squares for your IV, you add the 2 different errors that you end up with this sort of analysis. You got a sum of squares error within and a sum of squares error between. Which, again, if you really want to know what those things are, I'm happy to tell you. But the answer is find those 3 things, add them, that gives you sum of squares total, and then you divide the sum of squares for your IV by that, and it gives you the usual proportion of variability accounted for in the DV by the IV. So these 2 sum of squares errors come from different tables. These 2, there's like a within table and a between table. So you got to make sure to dig around until you get the right 3 things, which I'll show you on a later slide. And again, it just tells you the proportion of variability in the DV accounted for by the IV. How do you do APA format? For the Omnibus ANOVA, it's just like last week. For between subjects ANOVA, you got degrees of freedom for your IV within, degrees of freedom for your error within. You put the actual F value in there for Fisher, the guy who made this ANOVA test, to two decimal points, P less than or greater than, and throw your eta squared. Everything except eta squared comes right from your output, okay? For your Mauchly's test of sphericity, that also gets written up in the text. And it's a little weird. Mauchly's is, they use W to stand for Mauchly. Why it's not M? Well, that's used for mean. That's why. No one knows what a Mauchly's number means. So they convert it to its chi-square equivalent, which we'll learn about next week. And so you just got to fill this stuff in. And I show you again where to get this stuff so you can fill it in a later slide. So let's do it. Let's go ahead and run through repeated measures ANOVA worked example, and I'll show you where to get things. There is one you'll be not only analyzing but writing up, and repeated measures ANOVA is probably the most complicated stat we'll do this semester. So let's say you wanted to indeed do that study about the effect of annoying sounds on concentration levels, and every participant experiences all three of the really annoying sounds while they're trying to do some simple math problems, and you count the number of errors they make. And then you counterbalance the order that they get the annoying sounds so you don't get order effects. If you remember, think back to when we were talking about internal validity, you can't give them all in the same order. You got to mix it up. Some people get the screaming baby, then the tin foil, then nails on a chalkboard. You mix up the orders. That's called counterbalancing. So your independent variable is 3 levels. It's the annoying sound level. You've got crying newborn, nails on chalkboard, chewing tinfoil. And your DV is concentration level, and it's operationally defined as number of errors that people make on a simple math test. Each one is 50 questions, so they can make 0 to 50 errors. More impact on concentration is the inference. And the way the data are set up are kind of like the pair T were, except there's 3 columns in this case, right? So you got a column that's both the independent variable and it's the dependent variable score. So that's the number of errors that people made under crying newborn, number of errors that they made under nails on a chalkboard, and number of errors they made chewing tinfoil. And when you look across a row, it's the same person across that row, right? Under all 3 conditions. And here's the means, and I think the red box in the standard deviation. You need that, of course, for your APA write-up, so I'm just showing you where it comes from. But take a look at it. It looks like crying newborn and nails on a chalkboard, the means are really similar, right? They're both just about 13. And then chewing tinfoil is about 3 errors higher on average, right? And so note there's only 10 participants in this study. It's not a very big sample. What's nice about repeat measures designs is it's the same 10 people. It's not 30, it's just 10. So it's one of the benefits of repeated measures, is smaller samples required. So this thing's on the output. We'll talk about this during the next term, multivariate tests. I'm just going to keep going. Just remember to ignore this. All right, so the sphericity assumption, Mauchly's test, is the first thing that pops up after the means and after that thing I told you to ignore on your output. That's what it looks like. There's all sorts of crap in there, right? So let me focus you. That's your SIG. So where it says SIG under the Mauchly's table, that's your SIG. So is the sphericity assumption met or is it violated? Well, what's our rule? If Mauchly's SIG is greater than 0.05, the sphericity assumption is met. We can interpret the sphericity assumed results for the actual ANOVA. However, if Mauchly's SIG is less than 0.05, we've violated the sphericity assumption and we got to use greenhouse geyser. So it's just one or the other. We have met the assumption, right? Because 0.412 is definitely greater than 0.05. So we're going to be interpreting the line that says sphericity assumed in the ANOVA results. Hope that makes sense. So now let's go ahead and take a look at the actual ANOVA results, sphericity assumed line, and see if the groups differed. All right, so this is our Omnibus ANOVA that compares the same folks under the 3 different annoying sound conditions. Lots of crud in the table, right? It's really distracting. So this is, note there's a sphericity assumed line, greenhouse geyser line, and a couple others. I only teach you how to use the top 2 lines. Sphericity assumed if Mauchly's SIG is greater than 0.05, greenhouse geyser if Mauchly's SIG is less than 0.05, okay? So can we reject the null that the math error means, remember they were math errors they were making, are all equal across annoying sound levels? Well, there's our line, sphericity assumed. Note the source name there is annoying sound level. That's our independent variable. And have we met that? Here's our decision rule. If ANOVA sig is less than 0.05, reject the null. If ANOVA sig is greater than 0.05, retain the null. Is 0.002 less than 0.05 or greater than 0.05? It's clearly less than 0.05, so we're going to be rejecting the null. That is, the number of errors that they made on their math problems was not equal across the 3 annoying sound levels. All right, so the results suggest that the error means are not all equal for the 3 annoying sound levels. So it begs the question, that's an omnibus test. All we know is that at least one error mean is different from at least one of the others across the 3 annoying sound levels. Which one's different from which? Well, we got to do our paired t-test post-hoc tests using our Bonferroni corrected alpha level to determine specifically which means differ from which others. That's our post-hoc tests. So here's that. Here's our paired t-test post-hoc tests, and there's 3 of them, right? There's our means that we were comparing. For each one, we are going to use a Bonferroni corrected alpha level of 0.017 instead of 0.05. We're going to use 0.017. That's 0.05 divided by 3 different tests. And there are 3 tests. So here's the first one. Newborns versus nails on the chalkboard. We're comparing numbers of errors they made. And here's the paired samples t-test output. There's our line right there. We're going to use alpha Bonferroni of 0.017. There's our sig. So that's crying newborns compared to nails on a chalkboard. To the number of errors, that's at 13.3 and the 13.4. Did they significantly differ? Heck no. That is not less than 0.017. So they made equal numbers of errors for all intents and purposes under those 2 conditions, newborns screaming and nails on a chalkboard. How about newborn versus chewing tinfoil? This is hilarious. All right. So there's that one right here. Pair 2, crying newborns versus nails on a chalkboard. Again, we're comparing math errors. There's our sig. Is that less than 0.017? Yes. There is a difference between chewing, the errors they made when newborn was screaming noise versus chewing tinfoil. And look up there. Where did they make more or less errors? Well, crying newborn was 13.3. Chewing tinfoil was 16.8. They made more errors when they were listening to someone chew tinfoil, right? Boom. So errors was lower, less than tinfoils, what I was trying to communicate there. How about our final one? Nails on a chalkboard versus chewing tinfoil. Did the numbers of errors differ? There's that comparison as our last row, and 0.002 is definitely less than 0.017, so that is a real difference. And again, which one's higher? Well, chewing tinfoil, they made more errors. It's 13.4 versus 16.8, so they made fewer errors when someone was scraping their nails on a chalkboard versus chewing tinfoil. So the overall conclusion is that listening to chewing tinfoil resulted in more errors than listening to a crying newborn or nails on a chalkboard. However, remember that first pair there was the newborns versus the chalkboard, and they didn't significantly differ. So they made equal numbers of errors under those 2 conditions, but fewer under those 2 conditions than someone chewing tinfoil, which is just an awful noise. So there is a means plot you get. This is the one you get out of SPSS. I believe I have made this APA format already. It starts at 0, doesn't have grid lines, etc. for pasting into your output. So remember, this was the findings. We found sig was greater than 0.05 when you're comparing 0.017 when you were comparing newborns to nails, but then it was less than 0.07 for newborn versus tinfoil and nails versus tinfoil, right? That was the results. And so looking at the means, if you're visual like me, you can see crying newborn and nails were basically flat. Chewing tinfoil was elevated relative to both of them. And so most errors were made when they were chewing tinfoil. They had equal numbers of errors, but less than chewing tinfoil for newborn and nails, right? So those 2 groups are equal numbers of errors, but they were both less than tinfoil. So tinfoil, they made the most errors. That is the most annoying sound. It wins. So you have to make this figure that you get out of SPSS. Looks like this one right here on the left. This little tiny one, and it's clearly not APA format. You got to clean it up. You got to fix the axis titles. They have to be real words. Your axis titles, not squished together variable names. You need to start your y-axis at 0. No title above the figure, that estimated marginal means measure. You got to just get rid of it. You want to have real names for your levels. Instead of 1, 2, 3 at the bottom, note I put in crying newborn, nails in a chalkboard, and chewing tinfoil. And get rid of your grid lines if you got them. You can also stretch this out so it's a little bigger. That's nice. And then you need to copy this as a pic and paste it into the example APA write-up when you write it up. So make sure you modify the chart as necessary and paste it in. So you need to ignore the contrast table on the SPSS output. This is another thing that it spits out that confuses people. It's scary looking. It's got the word quadratic in it. We don't ever use this in this class, so don't worry about it. So make sure to ignore that. So the ANOVA results that you need for your APA write-up, as I said earlier, are spread across 2 separate SPSS output tables. You've got one called Tests of Within Subjects Effects. That's the one we were looking at earlier. You need that one. And then there's also later on this other little table called Tests of Between Subjects Effects. That's where that between errors at, the 122.167. So you got to find both these tables on your output in order to complete your ANOVA summary table. So your measure of effect size, again, is eta squared. It's pretty darn straightforward, except for getting the SS total. You got to dig around to both tables to get that. So remember, SS total is, there it is. Let me show you where I got stuff. So 7.94 is the sum of squares for the annoying sound level. That's your IB. Sum of squares total is the sum of squares for that independent variable, so that same number, plus the sum of squares for error within. You just use this, like if you use sphericity assumed, you'd use sphericity assumed. So same number. Error, and also the between subjects error, which comes from this other table at the bottom here. So showing you specifically where stuff comes from. Those are the 3 numbers. That was your IV, that was your error within, and that is your error between. You need all 3, add them up, you get 285.5. That was sum of squares total. Divide 79.4 by that, you get about 0.27, which is about 0.28, right? So what's that all mean? Well, it means that about 28% of the variability in math errors could be accounted for by what annoying sound level is playing. That is the independent variable. So to get Mauchly's, because you got to, it's in the text in the APA write-up, so you need this as well. This is the Mauchly's output from earlier, repeated, and that is the general form that you got to fill in the goodies on. I told you a lot of this stuff, who knows what it is. This would be it all filled out properly, so let me show you where this stuff comes from. Your Mauchly's W comes from where it says Mauchly's W, and again, no one knows what it means, so just put it in there and round it to 2 decimals. And so they give you the chi-square equivalent of that Mauchly, because people are more familiar with that, even though you might not be. You will be after next week. Degrees of freedom of 2. The 10 is your total number of participants, which was 10 in this study, right? You just got to find that somewhere, or maybe it's in the my example where I talk about the study. That is your chi-square value. It's like a T or an F or anything, just round it to 2 decimal points. And then finally, you got P greater than 0.05, right? So your sig was greater than 0.05, so you put P greater than 0.05. That's it. That's where you get all the stuff. But remember this when you're trying to do your write-up. So your APA format for the repeated measures ANOVA itself, you got this one table called Tests of Between Subjects Effects. You can actually get all the goodies for just writing up the ANOVA. Say it's in a sentence and you wanted to put it at the end of a sentence. The groups significantly differed in numbers of errors made, comma, F, blah, blah, blah. This would be that presentation, 2 and 18. I'll show you where all this stuff comes from. So degrees of freedom of 2. Your error within was 18. Your F value to 2 decimal points. Sig was less than 0.05, so P less than 0.05. And then finally, your eta squared came from that calculation on slide 18. However, we rarely write ANOVAs up in the text, particularly ones like this. We usually do an ANOVA summary table. So I'll show you how to do that on the final slide. So your ANOVA summary table is created by taking stuff from these 2, separate tables and putting them into a single table in your example APA write-up. So you gotta put it into this sort of format, and note this is divided into 2 sections, a between subjects section and a within subjects section. So the within subjects effects stuff goes in the within subjects effects section, between into between. And so there's your between stuff. You just copy it in like that, 122, 9, 13.57. And your within stuff goes into the within section. I think it's straightforward for the most part, except for the following. You use a star instead of putting a sig column if your sig was less than 0.05. And if you end up using greenhouse geyser because you violated the sphericity assumption, you round the degrees of freedom to a whole value. So if you look up above in the table, there's 79.4 and 83.9. You would actually round those for presentation in this table to 79 and 84, right? In addition, when you do that total degrees of freedom at the bottom there, you don't use the greenhouse geyser ones. You just add up the sphericity assumed ones. So you do 2 and 18 and 9 is what you'd be adding. You wouldn't add the 79 and the 84 and 9. So always use the sphericity assumed degrees of freedom for that total at the bottom of the table. And that's it. So I hope you enjoy doing this one. Hit me up again with questions if you need anything, and good luck doing your assignment.